So I thought we would start by looking at the self-exam. And I didn't know this would throw people quite as much as it seemed to. One of the things that was there... Did somebody have a question? One of the things that was there was to ask you... Well, I gave 2 questions. Maybe we'll go over those first, and then we'll talk about the next one. So, first question is, what is the general formula for the number of strings produced by a given number of bits, say in bits? And I think most of you could look at this video, and you could see the answer to that was in the lecture itself. So, what is it? Anybody want to offer it to just get us going here? If I have in bits, how many strings do I have? That's a good for venturing in. 2 to the power of n, right? So number of strings equals 2 to the n, where n is the number of bits. Little n is the number of bits. Big N, or this is the number of strings. So you get a lot from a few bits. And it's because they can be combined together. Like the switches that you saw in the video, you can have one switch on, one switch off, and so on. Okay. And then the next question was, suppose we don't have bits. Bits are binary things that can either be one way or another, and that's all. It's either yes or no, it's either on or off, it's either forward or back. But suppose we have a 3-valued thing, like a switch, that could be in one of 3 positions. Imagine a light switch that had 3 choices, not just on-off. So, what's the number of strings for a trit? Trit. Bit was 2 states. Trit is 3 states. So now you've got 3 choices, and the question is, what's the number of strings for 3 states? Any offers? Yes?
3 to the power of n?
It's 3 to the power of n, and it's important to see, well, why should it be that? Can you guess what it'd be if we had m states?
M to the power of n?
That's right. M states, it would be m to the n. Now, one way you can think about this is, let's go back to just the two. So I've got these 2 switches. So I put the first switch into the first state, and while it's there, I've got 2 choices for the second one. So there's 2 choices right there. Then I put it in the second state on the first switch. I've got another 2 choices on the first switch. So we got 4 altogether. Now if you try to do the 3, put the first switch into the first of the 3 states. Then you go 1, 2, 3 on the second switch. There's 3 of those. Move this guy over to the second position. You get another 3 here. Move it to the third position. You get another 3 here. So it's 3 to the n. Now, let's see what the next question was. Oh, okay. Here we go. Make up a problem that illustrates the world of bits and information along the lines of the above problems. Everybody, I don't know if does anybody have? Did anybody come up with something? Nobody did. Everybody just kind of fell apart on this. And true. It's probably asking something of you because it's asking you to be a little bit creative. But, I mean, I was trying to think, how would I answer this question? I might have not done any better than you some years ago. But I thought, well, at least somebody could have said, I have a cat named Kitty. Well, wait a minute. We had a question that I didn't put up there, which was to write your name in ASCII code. And I think most of you got that right. Most of you did that. Is that correct? Mm-hmm. So that worked pretty well. That went through. You could see how your letter would be come out written in bits. And then what you might have then done to make up your own problem is say, well, I have a cat named Kitty, and Kitty's name in binary, in ASCII code rather, is this. And you could have done the same thing for Kitty that you did for your name. So that was something that would have been possible. And then you could have done any number of names. But and don't feel badly that you didn't think of this, but take this as a kind of little stimulation of the kind of things you could do and the kind of directions you might want to think in. You might have said, I have a cat, its name is One. I can name my cat One. My cat's name is One. Not O-N-E, the word one, but the numeral 1. So here's my cat's name. It's One. And you want me to write that in binary? Okay. I need only one bit and one string to write that name. So I'm going to code the 1 into one of the two states of a bit. The bit has two states, 0 and 1. So I'll pick the 1 state, code my cat's name in 1. So whenever you see this 1, that's the name of my cat. It's 1. That's a perfectly valid answer to this question. And you can say, well, what about the other state, the 0? Well, I don't need that if I only have a 1-bit name for my cat. I don't need it, but maybe I could have 2 cats. So I'll have 2 cats. And maybe my other cat's name will be 0. Now I mean this to literally be the 0 of the counting numbers, just like this is the 1 of the counting numbers. This one over here is the name of a state of a bit. So I'm going to code my other cat's name in the other bit, in the other state of the bit, the other state of the bit. So cat 0 is going to be in this bit. That's fine. So by having a simple name for your cat, you get a simple answer to the problem. You don't even have to go to the translation tables for ASCII code or anything like that. But here's where this could really be, you could really demonstrate how deeply you understood this problem. You could say, well, I have my 2 cats, 1 and 0. Those are their names. Look on their collar, it's got a 1, and the other guy's got a 0 on his collar. I'm going to code the 1 into the 0 state of the bit. And I'm going to code the 0 into the 1 state of the bit. That's perfectly valid code. So that whenever you see a 0, that means the cat who's got the 1 on his collar. And whenever you see the 1 bit, it's the cat that has the 0 on its collar. So that would show that you can distinguish between the names of the bits, states, and the meaning that you assign to them. Because the code, remember, is about assigning meaning. So that would be a great answer to this question. And do not feel bad if you didn't come up with this answer. I wasn't necessarily thinking of any particular answer. But feel free to push back feel free to say, well, on the next question, I don't understand this question. And some of you did. That's perfectly fine. But this is one of the things you could do when you're asked to make up a problem, is to think about a problem you could make up and then solve it. I have to tell you a story about Eric Smullen, who was a very well-respected oceanography at MIT when I was there. And Eric tells the story of when he was a graduate student studying for his qualifying examination for his advanced degree. So he's a very young student, and he's a very smart guy, and he said, I got all my books together, and I had a little cabin, and I went out to the cabin with all my books and all my papers, and I was going to make up questions, and then I was going to answer them. So he started making up exam questions, as if he was now going to be the examiner. And he found that just about every question he made up, these would be questions in fluid mechanics and in mathematics, basic math and physics. Every question he made up, he couldn't solve, because the questions that are given in exams and the questions that people give in problem sets are so specially constructed that they're solvable. What he found, for example, was one of the things he wanted to do was, if you have a beam, like a bridge going across a stream, and you put a truck on it, and you want to calculate the forces that it's pressing down on the bridge abutments with, you can do that for certain kinds of attachments. Like if the end is free to float on top of the abutment, it's free to slide back and forth. It's not built in. And you can easily solve those problems, and you just sort of divide the force up based upon how far the truck is from the ends. It's typical that you can do all the time. But if you don't have that simplicity, and this is where Eric ran into trouble, if he had the beam built in, the beam is going to have to bend in order to calculate what the forces are. And that's a very complicated problem in structural mechanics. So that was his great discovery, is that when you try to make up problems, and now you can have some sympathy for your teachers, the problems have to be soluble in some way. And that's not easy to do. Okay. The essay question. Let's see. Now, everybody checked out on that. I guess students said, I don't know what this is about, and you said, forget it. All right. Well, first of all, I think it's good to be able to express yourself, to say something, and to be able to write it clearly, even if it's about math and not about literature or some other subject. So this was a question about the way the atoms and molecules that are in the natural world are pulled together in molecular bonds that basically make all of the structure that you see around you. And so I asked you to have something to say about that, or make a comment. I also did indicate that the way this happened, when we started with hydrogen and helium in the Big Bang, the hydrogen and helium slowly condensed into stars. The stars exploded in supernova, and that's when all of the heavy elements were made. Carbon, nitrogen. The only thing we started with was hydrogen and helium. So then you have all of the other things that you need in life that came to be when the stars started exploding. And then, once those cooled and started condensing, atoms and molecules are full of electromagnetic forces. that want to grab onto each other or shove each other away, and that's how the bonds are formed, by electrical forces. So they find each other and they bond. Or if they're heated up and they get too hot, the bonds will break. So what this question was pointing out was that's this dynamic that we're looking at in nature from the Big Bang up to the present. This is how things come to be complicated. This is how rocks and minerals first form by the condensation of various minerals, and then you get the first organic molecules, and then you get the first molecules of life, then you get the genetic code, and so on. It's a building up process, and it's really complex, and it took a long time because you do it little bit by little bit, just one tinkering at a time. So what's the kind of answer to that? Well, I thought of two answers that you could possibly have given. One is, I find this is really a little bit overwhelming. Quote, here's an answer. I find this a little bit overwhelming, and I don't feel I'm really equipped to answer this question, unquote. That's a perfectly fine answer, and you should feel free to give answers like that. Another possibility is a one-word essay. The word could be amazing, exclamation point. Or another possible answer is, I don't believe any of this. Perfectly possible answer. And I should have said very brief essay. I wasn't wanting you to write pages and pages about this. You have other things to do. So that's what I'd like to say about that, because I will probably ask more essay questions, and feel free to speak your minds. That's an opportunity for you to speak. The other thing I want to say, Marin, are you here? Thank you for writing cleanly. You labeled the questions. You wrote literate sentences about them. You did cop out on the last one, but that's okay. And I want to say something about presenting your work, presenting yourselves. When you write something, even if it's going to be sent over the internet, this is your craft. This is your self-expression. Take some have some affection for what you write. You want it to look nice. You want it to be accurate. You want it to be a form of self-expression. Take pride in your work. Don't just hand in a real sloppy paper. It'd be better to say, I just can't get this done right now, than to just slam something together. So that's all I want to say about that. Okay, let's start now to move on. Are we advancing with the arrow keys?
I think so.
Okay.
Give that a try. Here you go.
Okay. Well, I was going to say something. This is just another example of the answer to that question. This is just a simple skin cell. It has 10 to the 14th atoms inside, and it has a very complicated structure, even though it's just one of many trillions and trillions of cells that are in your body. And it's got 10 to the 14 atoms. Those 10 to the 14 atoms are really complicated strings, but basically the way they bond is coding those strings. The strings that describe the positions of those atoms are coded by the electrical forces of the atom, of the protons and electrons that are pulling themselves together. When they pull themselves together into one shape, that's basically like the cat in the one state. And when they are in another state, that's like the cat in the other state. And I just wanted to say that also deep inside the cell, now that cell you saw, which is just a microscopic skin cell, deep inside, it's mostly filled with stuff called cytoplasm, which is mostly water. But inside, there are all these machines running. And this is just a little picture of one of these machines. It's called a motor protein. And you can see it's got a foot, and it's pulling and it's tugging this cargo. This is not a cell. This is inside the cell. These are molecules. These are molecules that are doing this stuff. Now, this is a pretty complicated molecule, and if you look on the internet, you can actually find movies of these molecules walking. These are done by computer simulations of the actual electrical forces that are involved. And there's about 200,000 atoms in this little guy that's pulling this cargo along. So I just want you to know that all of this complexity ultimately goes back to atoms that have been coded in very special ways. And it's not trivial to make that code. It took 3.7 billion years to do it. Building step by step from the simplest little things to a little more complicated and so on. Okay, now let's get back to math. So we're going to build on our knowledge of strings. We're going to talk about infinity, the concept of infinity. So, where are we going to get infinity? We're going to get it, first of all, from the very simple things of counting numbers. The counting natural are also known as the natural numbers. 1, 2, 3, 4, and on. And I put an infinity symbol here. I normally don't like to do that, but I'll put it here because infinity is not really a number. It's a concept. So, just to give you the sense that this string is an infinitely long string, and the elements in it are the natural numbers. Well, the set of counting numbers is infinite. That means it's boundless. That means it never ends. When you think about it, it's a little dizzying to think about, but that's what it means. If you give me any number, make it as big as you want. I'll add 1 to it, and I'll make one that's bigger. That's what I just said. So, when we're going to talk about infinite and infinite sets, we're going to use the counting numbers as like the gold standard. The counting numbers are what you go back to. It's like the measuring stick. That's why I put an underline on it. So when we're going to say something is infinite, we're going to refer it to the infinity of the counting numbers. That's what everything has to. If something claims to be infinite, it has to show how it's like the counting numbers. So, an arbitrary set is countably infinite if every element can be paired with an element of 1, 2, 3, 4, da da da. So let's right away have an illustration. Suppose to the counting numbers 1, 2, 3, we stick in 0. We want to have 0 in the set as well. We're going to have a 0. 0, 1, 2, 3. Which of these sets is bigger? Well, you're right to feel a little cautious about giving an answer. Suppose it was 0, 1, 2, 3, 4. Suppose it was 0, 1, 2, 3, 4. That was the set. And this was 1, 2, 3, 4. Which would be bigger? So if they're finite, we can always count them and find out. The problem, we can't compare these because we can't count out to the end. So a finite set can always be compared because just count up what's in one and count up in the other and compare them. but we're stuck because of this infinity. Now, I added a 0 to this set, which is otherwise looking just like this set. It turns out these sets, if we follow the rule of every element has to be paired with the gold standard. So what we do is go up to the set that we're trying to find out if it's infinite or not, or if it's the same size as this set. We find the elements and pair them one at a time. So now I'm going to pair the 0 with the 1 here. I can do that. I could have called these, well, put the 1 with the 2 with the 3 with the 4. I can keep going. The fact that these are infinite means that there's always a fresh supply. This is the kind of bank account you want. There's always a fresh supply of numbers. So I just exhibited the pairing, and there's no point in my doing 6, 7, 8, 9, 10, 11, 12. I will always be able to find a mate. So infinity plus 1 is still infinity. And that's the kind of crazy thing that happens when we do infinite sets. It could be infinity plus 10 or 20 or anything like that. Any finite addition to an infinite set still keeps it the same size because of the fact that we could always find a mate. Let's try something a little harder. Let's look at the odd and even numbers. So 1, 3, 5, and 2, 4, 6. So we have two sets here. Now, if I pulled out half the numbers, so it seems, by only having the odd numbers or only the even numbers, if it was a finite set, they would be obviously smaller than the full set of the counting numbers if it was finite. This is what the funny stuff that goes on with infinity. If we follow the rule of pairing, let's take the odds. I'll put the 1 with the 1. I'll put the 3 with the 2. I'll put the 5 with the 3. I'm never going to run out. So the odd numbers and the evens, I can do the same thing with the evens. Put the 2 with the 1, 4 with the 2, 6 with the 3. I will never run out. So there's just as many odd and even numbers as there are all numbers. Try to get your arms around that. So what this is saying is half of infinity is still infinity. I should perhaps put this in quotes, but that's the kind of interesting thing that goes on with infinity. Now, let's try the integers. Do you know what the distinction is between the integers and the natural numbers? This is the place to probably learn it. The natural numbers are the 1, 2, 3, 4, blah, 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 blah. The integers are all of those plus 0 and all of the negatives, all the negative numbers. So these are the integers. But there are no fractions. That's why they're called integers. There are no fractions. They're all whole numbers, but they include 0 and the negative numbers. So these are the integers. Well, now, if you look, looks like we've added a whole lot here because we threw in the 0. Well, that was not a big problem, but I've thrown in a whole other infinite set of numbers here with the integers. So I want to show you what's a really beautiful proof that the integers, which have an infinite number here and another infinite number here and a 0 thrown in the middle, that this big conglomeration is still no bigger than the countable numbers. Here's how it goes. I call it the cobweb proof. Can everybody see this? All right? So here's how you do this. Go to the 0 and start there. So what we have to do is pair every one of these numbers with one of these guys. So if you imagine, see if you can imagine this set kind of strung out along this path that I'm creating here. So from 0, I'll put the 0 with the 1 with the 2, minus 1 will go with 3, 2 will go with 4, and you can see where we're going. So by the time this cobweb works its way through both the negative natural numbers and the positive natural numbers and 0, everyone will have been covered. Everyone will have been mated up with one of the counting numbers. That's kind of stunning, actually. So this says that infinity plus infinity equals infinity. Infinity here, still the same sized infinity of the counting numbers. Now we're going to do one more step. Suppose we have an infinite number of integers. So here we have one set of integers. But suppose we had 3. Here I've got this set of integers, I've got this set of integers, and this set of integers. I've got a lot of numbers here. So suppose we had 3. Well, I'm going to go all the way to the limit here and say, suppose we have a countably infinite number of these things. Like that. Now, surely this is really going to blow the roof off, and these are not going to be countable. Surprisingly, they are countable. And the cobweb proof can come back here for you. Just like before, here's the cobweb working its way through. So it's paired this number, it's got this number, picked up this one. Now it's picked up these 3. It's gone over here. And you can see that this cobweb will slowly work its way through and eventually pair every one of this infinite number of infinite sets with the counting numbers. Now, I think it's... so what we end up here with is we found that infinity plus 1 is still infinity. Infinity plus infinity is still infinity. A half of infinity is still infinity. Infinity times infinity, that's the last one we just did. We have infinity times an infinite number of them. That's also countably infinity. And there's one more operation that I haven't said anything about. That's, what about 2 to the infinity? What is that? What would that mean, and is it countable? And the answer is, it is not. 2 to the infinity is not countable. That means if you start forming the powers of 2 times for a growing number of terms, you will not be able to pair them. You will run out of countable numbers. So this is a very big deal. And it's, you notice it's exponential, right? It sort of says, when you hit exponentials, things get really big, and they get big so fast that they really aren't countable. Okay, now,
Can I ask you?
yeah, what we want to do now, I want to stop here and try to consolidate what we've been talking about.
My question is just around how would you prove that?
You know, this wasn't proved until the late 19th century, or 1880s, around in there, by a very famous mathematician named George Cantor. And we're going to do that next time. There are not very many proofs in mathematics that are simple enough that you can do in an introduction like this. and I hope these have not been. I hope the cobweb was not. I think the cobweb. You can see that. You can do it. You may have to go back, look at the video again, try it out yourself to prove it. But Cantor's proof is ingenious and beautiful. And it just involves a diagonal line, and we're going to do that next time. So, now, how do we set these ideas? Make sure we've got them. How about a question? So, this was the result of our work this morning. All summarized right here. Well, you have to take my word for this. We didn't work on this. We're going to do that next time. Any questions? The thing to keep in mind and to remember is this is all based on the idea of finding a mate to the counting numbers. Yes?
If you did like infinity divided by 1, would it still be infinity?
Yes.
But if it was infinity divided by infinity, you're back to 1?
Infinity divided by infinity?
Yes.
That's really... Remember I said I didn't like putting infinity in the line of... You're assuming that infinity is a number. And this is... I apologize because this is so cartoonish, but infinity is not a number. It's a concept. And when I say a half of infinity is equal to infinity, what I mean is a half of the countable numbers is still the same size set as the countable number set itself.
So you can only do...
So when you say infinity divided by infinity, this is not defined. This is...
So it can only be divided by...
You have to be more specific than that.
So you can't...
But infinity divided by 1, that's pretty straightforward because you divide every number in the set by 1 because you're thinking of infinity as the name of the counting numbers. But even that's not quite correct. So be careful when you try to manipulate or play with infinity because it's not a number. So what's the main thing you keep in mind when somebody wants to talk about infinity? What should immediately come to mind?
It's not a number, it's a concept.
Speak up loud. Can't hear you.
It's not a number, it's a concept.
That's good, yes, but something else. Something else. It has to be paired with the countable numbers. The pairing with the countable numbers is the key idea of infinity. So if somebody wants to start talking about infinity, you should immediately says, that's got to do with it mating with whatever this thing is that's infinite. I have to be able to mate it with the counting numbers. That's what should come into your mind.
And can I ask you guys, are you clear when he says that, what he means?
If you have some set and you're not sure if it's infinite or not, you have to be able to prove or show, like we did with the cobweb proof, for example, that every one of those elements in that set can hold hands with one of the counting numbers.
Or get labeled. I mean, you could write a label on it.
Right. Or an arrow from one to the other. That's what it means to be paired. Hold hands. Label.
I really like the elegance of the way you use that cobweb design. It's, to me, it's a symbol that it's a series of lines moving in a certain way that creates a symbol, and you call it cobweb. I get that, but all the numbers themselves are also symbols. They're standing for something.
Right.
To me, I was getting a little lost when you were just putting up those long strings of numbers, but when you brought that symbol that was not in the number form.
You mean the web?
Yeah, the web.
Yeah.
There's something about that for me that
Oh, I think
That
it's
elegant.
enormously helpful.
And is that at higher complex math? Is that normal to be able to do to bring in?
I think it's essential.
Okay.
Now, there are some people who think so abstractly that visualization like that doesn't mean much to them. And a lot of them are mathematicians. I'm very visual, so it's really important to me to kind of see how you actually could line up every one of this infinite number of infinite things, actually get them all to turn out to have a mate with the counting numbers.
Right.
And so you think of the counting numbers as basically streaming along that web.
Yeah. No. Again, that was what was brilliant about it. I finally got it when you did that.
Great.
Is that cobweb concept or principle your unique idea, or is it something?
No, I don't think it's unique to me. But it's not. If you go on the internet and start looking, trying to find out whether a countable infinity of countably infinite sets is countable, this doesn't come up first. You have to kind of look for it. So I was talking there kind of gibberish almost, but here's this infinity that we've been talking about. Oh, I know. This is what I want to show the next slide. So, well, I've already told you that 2 to the infinity, again, that's a kind of cartoon. Infinity is not a number, but exponentiation of infinite sets is a greater infinity than countable infinity. And here I want to go back. There is more than one kind of infinity. I mean, it's sort of like you come into the world and then you learn there's sex. It's like, how could that be? I mean, some infinities are more infinite than others. Some infinities are more infinite. And that 2 to the infinity, exponentiation, will create bigger infinity. And that's what we're going to talk about next time. So now that's the new material that I'm bringing today. Let's now have any questions or I have another illustration I want to do. We're going to need Wolfram alpha for this. We're going to do another problem to just kind of reinforce what we've been learning up to this time. So here's another question. Have any of you played with Wolfram alpha? We're going to have to do do a calculation where you're going to have to calculate the log. And I'm going to show you how you can calculate the log in your mind and hit it pretty closely. So, how many bits to encode the English alphabet? How many letters in the English alphabet?
26.
26. Shout it out. Okay. Do we need 26 bits? No. Well, how many do we need? they're bits, so they're binary. We're not talking about trits or quadits or four-state things.
13.
Loud.
13.
Well, that's a good answer. At least it's less than 26. 5. Who said 5? That's close. Okay. Well, how do we think about this? Let's first of all ease into this. How do we think about this? What's the relationship between strings and bits? First of all, let's start by saying a letter of the alphabet is going to be a string. The code for a letter of the alphabet will be a string. Okay. And we need 26 strings. And the question we're asking is how many bits it would take to do that. So what's the relationship between bits and strings? We've been at this early this morning. How do you relate bits and strings? Somebody please say it again, even if you're...
2 to the power of n.
2 to the power of n, right. So the number of strings now in this case, what we want to know is the number of bits for a given number of strings. How many strings do we have? 26 strings. Each letter of the alphabet is a string. A is a string, B is a string, and so on. And they're actually going to be, in binary, they would actually have several bits if you had them as bit strings. So we have 26 strings. So what we're looking for is the value of n, the number of bits, so that when you exponentiate 2 by n, you get 26. How do we calculate this? We want the n. How do we get the n? We want to kind of find the inverse of the exponential function. What is that? It's the log function. Log So if you take the log of something, it grabs the exponent for you. Now, there's an issue about bases, which I won't talk about right away, but the log function will pull the exponent off whatever number you apply it to. So we would like to pull this in off that 2. So what we want to do is log 2 to the n is equal to n. So what we want to do is take the log of both sides of this equation. So log of the number of strings, which is what we're looking for, we're looking for n, is equal to n, where the log, I'm going to now write a 2 here, we're taking logarithms where 2 is the base. Or let's just make it simpler. Imagine there's no other base in the world except 2. Don't worry about something called e or base 10 or any of that. The only thing in the universe is 2. 2s are everything is built out of 2s. We're in the binary world. So n is actually the log of the number of strings, which is 26, right? So if you want to use Wolfram alpha to find what this is, you put in log 226, which is, because there can be different bases rather than 2, you can put in you have to put in what the base is. So log 226. Anybody have their laptops open? It's really important that you be able to do this. So you have, okay, good. It's working. It's working. You got it.
4.700439.
Who said 5? Who said 5? Oh, that was you. Okay. Okay. So how many people were able to at least get open to the page with Wolfram Alpha? Great. Okay. And go ahead. We'll take some time. So go ahead and get log of 2. Log to base 2 of the number 26.
If you have a phone, you can also access it.
Yeah, whatever, tablet, whatever. I'm going to wait because I want you to be able to use this thing. It's kind of, we've kind of gone past the time to take a break, haven't we? Okay, this is going to be informal. Just kind of chill out while some people work on this, but I would like everybody in the class to try to find out what the answer is that they get for this. And we're just going to chill out, take it easy.
I would want more digits than that.
You'll never get enough digits.
It doesn't even start repeating at a certain point. Like I'm not able to find a point where I see a digit and it starts repeating. So to get more digits, it starts repeating.
Let's see if we can.
Do you have a tab for it by any chance? Or?
I don't yet.
Okay. Okay. While you're working, I'll answer a question. Somebody's asking, how many decimals are there? How many? It depends on what the number is. But some logs are going to give you infinitely many decimal places. It'll never terminate. It'll go on forever. Those numbers are said to be irrational. How'd you do?
4 points.
Okay. Yep, you're on. Okay, is everybody pretty close to being there? Everybody's good? Okay, so it's 4.7 something, right? Well, how do you do 0.7 bits? Well, what this is you need 5 bits.
Yeah.
Okay, now,
How many of the possible code options do you not use? Because I think it's just one. I could be wrong though. Like, with 5 bits, how many?
you're going to have something left over? Is that what you're thinking?
How many unassigned options do you have left over?
Well, with 5 bits, you have 2 to the 5th strings, right? So you're going to have, you can calculate that. It's 2 to the 5th minus log 226. Or, I'm sorry, it's 2 to the 5th minus 2 to the 4.7, blah, blah, blah. 2 to the 5th minus... So you can get an approximation. But remember, the bits are discrete. So you have to round things off to the nearest whole number. So you'd need 5 bits. Okay. Yeah. Is everybody okay with that? Okay. Now here's something I would like to ask you all to remember for the rest of your lives. Remember this. Whenever you see a logarithm, and you want to know what the log of that number is, count the number of digits of the number. That's about what the log is. It won't be exact. So if we have a number like 5, can everybody see that? 572634. Is that? Did I write it too small? Can you see that? What's the log of that? Well, you've got your Wolframs open, so you can calculate it. But before you do that, following this rule, that the logarithm is approximately equal to the number of digits it takes to write the number, which in this case would be what? About 6. Well, see what it comes out to be. Yes?
Could you write down what you said to remember for the rest of our lives so that we can write it down?
Okay. First of all, whenever the word logarithm comes up, logarithm, your mind should remember this fundamental trick, fundamental power that you will now have, that the logarithm of any number is approximately equal to the number of digits it takes to write the number down.
Assuming base 10, right?
Actually, it's close because 2 is not that big a difference from 10 when you're... So the closer the number is to something in base 10, the more accurate it'll be. But it'll still be pretty good. So I don't know. I just made that number up. What do you get?
You get 5 points.
Is this in base 2 or base 10?
It's 10.
10, okay.
You get 5.757877 on and on.
Okay. No. That's too much. What did you get? 5.78? And what did I say it would be? 6. You know, when I was a student in high school, this was before computers. All we had were slide rules, and we had tables. And when people would teach you logarithms, they would teach you how to look up these things in the tables. They were incredibly complicated. You had to find the mantissa, and then you had to find the whatever, and it was just a nightmare. It was like I had a feeling like you could have had. I don't want to have anything to do with this stuff. It's horrible. But if you remember that the number of digits is about the value of the logarithm, that's really interesting. How are we doing on time?
We're at 11:32.
Okay. Well, I'll have a new announcement that will come out, if all goes well, this evening, and it will have a new self-examination to see how well we understood this material. And God willing, we'll meet next week. It will probably be our last talk about infinity. And then following that, we're going to go to mathematics and art. All right.